So I only have a limited amount of what we're going to cover eventually on risk and return. Part of it is I don't want to introduce the new topics of things like the capital allocation line, the capital market line, things that get a little bit more advanced, and then have you be tested on them 1 week later. These are topics that I think need more time from you on your part to be able to fully comprehend, especially if you haven't seen these concepts before, to fully comprehend and understand them, time to practice them. And so that was also a part of why I'm not going beyond what I'm planning to do today, which is talking a little bit about risk and return. These are all the problems that I recommend from the chapter. They're not all of these problems are topics that I will be covering. So again, I will try and include that in the email, which problems you should focus on that pertain to the midterm exam material. Some key terms, and this is again all of Chapter 5 key terms. We're not going to talk about risk aversion and the Sharpe ratio today, I don't believe. I'm not planning on it. Yes, no, I'm not planning on that. It does have to do with a little more, that loops in more advanced topics. So we're going to be talking mostly about just measuring risk and return. We're not going to get into risk aversion. That's that, there's usually some squared component in there or variances in there. We're not going to get into portfolio allocation. I want you to have time for that to really sink in, give you a chance to practice it before I test you on it. So measuring risk and return, these are things that you have hopefully seen before this class. Things like holding period return. That's an unannualized return for a specific period that could be less than a year, it could be more than a year. So a 20% holding period return for a 2-year period. What's the annualized return on a compounded basis? You take the square root, subtract 1, 9.5%. The APR, you do a simple annualization of the holding period return. So let's say it's a quarter, let's for argument's sake, do monthly, a monthly return of 1%. APR would simply be times 12, 12%. If you get that, take it. It's my advice, at least in this environment. The effective annual rate, EAR. This is APR, this is EAR. This includes compounding. So if we are looking at, I'm going to pull up my calculator. An effective, so an annualized, an APR of 0.35, excuse me. Let's see, the monthly return is 0.35 times 12, that's 0.35%. So 4.2%. So that's our APR. If you're given APR, you divide by 12. If it's a monthly compounded, so it's 1.03. You have to add 1. You have to raise it to the power 12. N is the number of periods. So if it's a monthly period, N is 12. If it's a quarterly compounding period, N would be 4. So if I say, okay, you have, let me put it on a Word file. An investor has a product which pays 6.32 or 6.25% APR but it compounds monthly. What is the EAR? So first, figure out the monthly return. This is the holding period return. I'm putting the formulas because I'm going to post this to Canvas. So HPR is equal to APR divided by N. N equals a number. So my APR is 6.25%. Monthly, there are 12 periods. Let me pull up my calculator. .6.25 divided by 12. Okay, 52 basis points, 0.52%. Now, whenever I take an exam personally, I try not to clear out my calculator. I do have to divide by 100. Give me 52 basis points. So the EAR will be this formula here, which is the same thing as that, unannualized holding period return for this instance, because the holding period return is less, the period is less than a year. .0052. So I go back over here. 0.0052, that's the decimal point holding period return for 1 month, plus 1, raise it to the power 12. Sorry, I forgot to subtract 1. I'm so sorry. .433%. Now I might ask for 3 decimal points, so I'll just put that there. Usually it's stated per, I think that was a 0 there. 6.25. 521. You know, I will guide you. I will tell you how many decimal points to put in there. I try to incorporate a margin of error so that, you know, if it's just a rounding error, that the computer, the Canvas site will automatically give you a credit when you enter in your own number. On the exams, I do purely multiple choice. So that won't be a problem in the exam, which is what your final, you know, course grade is going to be based off of, predominantly your midterm exam scores, with the extra credit that I give you through how you perform on the quizzes. So that is APR, effective annual rate, And so that's why when you see, and when you look at, like for instance, credit card offers, they're telling you an APR because that's how they calculate their interest. But of course, if you hold a balance, that APR is much higher. So let's say you have a credit card offer that says that the current prime rate, because it's usually banker's prime rate plus a spread, it's an 18.5% APR monthly divided by 100 divided by 12 plus 1, raise it to the power 12. That's an extra 1.65 percentage point return for them on an annualized compounded basis. If you hold a balance. Now it accrues daily. It accrues daily, so they actually figure out what's the daily APR, what's the daily interest rate, and apply it to your balance, your daily balance. Now, they're very high. That's also because when an individual tends to go to bankruptcy court, files bankruptcy, the first thing that's done is the credit card debt is wiped out to fractions of what's owed. It's sent to collection agencies. So they're very risky for lenders as well because they get wiped out very quickly. There's no -1 on the slides as well. Oh, thank you very much. I'll have to fix that and repost it as well. Actually, I don't know that I posted the PDF of this yet. Calculating average returns. Any questions, any other questions on holding period return, APR, annualized percent rate, and EAR, effective annual rate? Thank you, Hussein, for finding that mistake. Okay. All right, so arithmetic versus geometric. I don't know how many of you have come across this, but they are very important. A lot of times people just say, oh, okay, well, here, let's look at these returns I have on the slide. Okay, we have 6.5, 4.5, minus 50, plus 50. Okay, so we're doing okay. We're doing pretty well. We made that money back. I've got another typo on the screen. That should be 4, 1, 2, 3, 4, 5, 6. It's a 6-year investment. What's the arithmetic return? What's the arithmetic average? It's a simple average. 6.5 plus 4.5 minus 50 plus 50 plus 5 plus 9 divided by 6. Fantastic. What's the geometric average? You will also hear people use the term compound annual rate, or compound annual return, or compound annual growth. Those are all geometric. This is in the textbook. How do we figure that out? 1 plus point. Okay, so 1 plus the return for year 1, 1 plus the return for year 2, 1 plus the return for year 3, which is minus 50%, 1 plus the return for year 4 plus 50%, year 5 is a 5% return, year 6 is a 9% return, put these around big brackets, raise it to the power. How many years? There are 6 years, despite it saying 5, that's a typo. Raise it to the power 1 over 6. So our calculator. 1.065 times 1.045 times 1 minus 0.5 is just 0.5 times 1.5 times 1.05 times 1.09. Oh boy. Raise it to the power of 1 divided by 6. And I forgot the minus 1 again. Minus 1. Quite a difference. Annualized return of 4.17 if you're doing an arithmetic average, whereas if you're doing a geometric or a compound annual rate, you're down slightly. Minus 76 basis point return per year during that time period. It's a bit of a mistake. When you look at this, and I'm going to, anyone who's interested in going into a more academic route, there's a very useful mathematics trick, where if you, as n increases significantly, and in math speak, as n approaches infinity, this term approaches that continuous compounding constant, e to the power of APR. Some nice features about that, that's if you do what's called the natural log, that's essentially what's that power, e to the power what? And so you can use natural log returns. And if you do natural log returns, if these were natural log returns, you could in fact just take the simple average of them. And that's why academic papers typically use natural log returns for their research. It's not what we use in terms of reporting, in terms of investing, because that's how we report compound returns, holding period returns. Change these. I'll fix the table. Any questions on arithmetic average versus geometric returns or compound returns? Okay. When we're looking at different forms of risk and return, we're going to have to understand what we mean by risk. And I'm pretty sure everyone's taken their statistics class that they had to take for their major, but I'm going to go through it again here. You do need to understand it. I'm not going to make you do continuous distributions. That's overkill, but you do have to understand the theory. Everyone, does anyone not remember doing variance and standard deviation from statistics? So I didn't prepare that. I'm assuming that everyone has that foundational study. So if you want me to go through that, I'll do that on the fly, but I hadn't planned on doing it. Okay, other than actually showing you an example. Okay. So first of all, just doing expected returns. What's the expected return when we have these four states of the world? 15% probability, we have a return of -4, 25% probability, we have a return of 1%, 40%, 8% return, a probability of 0.2 or 20%, we have a 20% return. What's the expected return? You just take simply the weights, you multiply across the rows, and then add them up. So 0.15 times -0.04. You work through this, you get the expected return. It's a very straightforward exercise. What's the expected risk? And what do I mean by risk? Usually, we do it using the statistical terms of variance and standard deviation. So the way that we measure, well, how dispersed is this set of realized outcomes, or the set of potential outcomes? How dispersed are they? We take this, what's called the squared deviations, and we weight them by their probability. So 15%, the return is -0.04. The expected return is 0.0685. So the distance between -0.04 and 0.0685 is -0.1085. You know, -0.04 minus 0.0685. We keep on going to each one. So 25% weight, return of +1%. How far is that from the expected return? Take the squared deviation and move on. 0.4, what's the deviation from the expected return? Take the squared deviation, move on. You sum them all up. You work through all of this. You get a variance of 0.0613%. Standard deviation is a way to bring that squared deviation into a similar dimension as returns. So the standard deviation is simply the square root of variance. That's 7.831%. Does anyone have questions about how expected return, variance, and standard deviation are, how they are calculated, what they mean, and why they're important? there is an aspect to, essentially all of, all social sciences, they almost all of them use a specific relationship between expected value, the mean, and the variance. I have here the coefficient of variation and the Sharpe ratio. I'm introducing the terms here, but I'm not going to have them as part of the exam material because I want to really fully explain why they're important. I really need to get to the portfolio allocation and portfolio theory before I can do that. But these are ways that investors can, in fact, measure their risk with respect, relative to the amount of return they're getting. All right, so yet another form of dollar-weighted return. Now, this is probably something you would have gone over in kind of like a business accounting class. It's the internal rate of return of these cash flows. So the initial outlay is 500. The subsequent outlay 1 year later is another 100. Then you get 100 cash flow back, 200 cash flows back, 200, and 300. In Bodie, Kane, and Marcus, they call this the dollar-weighted return. So this would be, you put in 500, you add an additional 100 to your investment, and then you cash out 100, 200, 200, 300. And then the investment's done. Now, in order to solve this, you do need access to a financial calculator. I'm pretty sure you're not going to be able to do it on the calculator you have in Canvas. This is an NPV, absolutely. And so I may put a question like this on the quiz for your practice. I don't want to necessarily, I am hesitant to commit to putting it on the exam now because I need to be sure that everyone has a financial calculator and knows how to use it. And like I've said before, me testing you on understanding is different from me testing you on how to, whether you know how to use your calculator. I think there is a way that I can put it, since the exams are multiple choice, that I can put it on the exam and it would work out. So thinking about it more, a question like this would be a candidate for the exams. I wouldn't take it out 10 years, but. So does anyone want to, let's take a minute, see if you can figure out the solution on your own. I'll set a timer for 2 minutes, and then I will ask for people who are willing to actually share their answers. So don't share your answer until I've given you the go ahead. All right, I think everyone's had enough time to do the problem. If you're taking more than that, it means you probably need to practice using your financial calculator a little bit more. Don't worry about that being a hindrance on the exam. I will keep that in mind in terms of how to formulate the exam, that I won't necessarily ask the question in a way that you need a financial calculator, just in case. Does anyone want to share their answer that they got in terms of the return for this cash flow, this investment? I'm wondering if anyone did the problem. I'm just hesitant to share. If you are, let me try to pull up the interest rate is what you need to find. Initial outlay of 500, additional outlay 1 year later of 100. What you have to find is the interest rate that gets this equation to tie, to equal 0. And so let me let's see, cash flow, TI. So, oh man. Here, cash flow in a BA2 plus. If you're using the HP version, you just Google it, and there are lots of YouTube videos that show you how to use it. So if you don't like reading through the manual, which is what I did, although that was many years ago, so I've forgotten how to use it, and I've lost the manual to my BA2 plus. But there are plenty of YouTube videos that you can get access to for free. So, I mean, you just have to have an internet connection and a computer or a cell phone. The way this has actually worked is it's solving this problem. It's solving this problem. And so let me pull up my file. If you don't have a financial calculator, but you have access to Excel or some kind of a spreadsheet software, IRR. Well, so the question is it's an IRR, not an NPV. To me, they're related. It is. So I guess that is yes. That was my mistake for not being more specific for using the cash flow buttons and then calculating the IRR from that. But the NPV equals 0. What's the return? What's the interest rate that gets you this string of discounted cash flows to equal 0? And so the formula in Excel is IRR. In a BA2 plus, you have to type in all the cash flows and then calculate the rate of return. A question about what's the best resource to use when learning and practicing on the financial calculator. It depends on what you're doing with it. So I'll give you, me personally, I pulled up a lot of problems. I was using it for CFA exams, so I just essentially pulled up a lot of problems and saw the ones that tend to come up most frequently, and made sure that I took time to actually not study the material, but study the, how to make the calculator do what I wanted it to do. And it takes time and practice. And the reason why I did that is because I knew that I had to know how to use it in a timed exam setting. And the way that I, philosophically want to run my classes, I don't want to test you for being able to use it. So that if you are using just essentially a calculator that looks kind of like this, you can still get the right answer. But that's not necessarily the case if you're interested in going and doing trade examinations, any kind of securities license examinations or the like. So you will have to learn how to trick your calculator to do what you want it to do. So 8.15%. Yeah, I hope so. That's what I've got here. All right, so these kinds of questions, like these kinds of problems, come up more frequently in a management accounting class when you're trying to figure out which project has the best IRR, but then you also have to consider which project has the highest NPV. You may have to put up more capital, but it will contribute more to the bottom line in terms of dollar amounts. But there are ways of measuring returns in finance and investments based on dollar weighted return, which is IRR. I'm going to spend a few minutes. We'll take a break right after this, and then we'll come back to just talk. I'll field questions about materials and about the exam. I have not written it yet, so I can't tell you how long it is, but I'll tell you I'll remind you again how I create it. All right, so value at risk. This is something that is useful for a lot of different practitioners, whether it's some kind of a fund, a family office, a private investor, and very frequently trading desks at markets operations units at all the different large financial services companies. Value at risk is essentially a percentile. It tells you, and it varies based on preference of the organization or the individual, but it's usually 5% or 1 percentile lower tail. So when they say, what's your value at risk? What's your VAR or VAR? And you hear a number. Let's say it's 50 million. And then you say, well, what's the percentile? Well, you're using 1 or 5. 5. 50 million is the 5th percentile, and it's 50 million with a minus sign in front of it. Our 5% worst outcomes that we should expect on a daily basis are losses in excess of 50 million for a day. That's what this measure is. And most calculations have some assumption of a normal distribution. Not all, but many do use some assumption of normal distribution, whether it's log normal, so natural log returns, so to speak. Has anyone here not seen a graph of the normal distribution, the bell curve? I do have one later, but I would rather pull one up from Google just to make sure. Okay. If we think about the normal distribution, and if we say, okay, if we look at the S&P 500, and we say that its daily returns follow a normal distribution, has anyone come across this, assumption in whether it's in classes here at UNCC, or in your studies, or in reading and other things, you come across this idea of daily returns of the S&P 500 being normally distributed. No one's come across that. Okay. Never explicitly said, but implied. Yeah, it's fair. There are a lot of very famous models for asset pricing, and they assume normal distribution. One of the most famous is probably the Black-Scholes-Merton options pricing model, or the Black-Scholes options pricing model. If the S&P 500 is in fact, the daily natural log returns or the regular returns. I use natural log, but you'll come to the same conclusion either way. If it is normally distributed, then since the S&P 500's inception, since 1950 or so, there should only be about 1.6 instances of daily returns that are outside of 4 standard deviations away from the mean, up or down. The standard deviation, that's that measure we were just looking at. Variance, take the square root of variance, that's a standard deviation. And we can use that unit to tell us the dispersion in the same dimension as our linear returns, our level of returns. And so that means you should only expect a 4 standard deviation move, whether it's the upside or the downside, about once every 63 years. In reality, we actually have them about once every 6 months. We've had 190. So things aren't normal. There are lots of researchers who have won Nobel Prizes based off of this, assumption of normality. There's a very famous economist who created a correction for the fact that we have these, periods of heightened volatility that seem to violate the assumption of normal distribution, and he created what's called an econometric technique. It's called ARCH. Well, ARCH is the theory. GARCH is how you correct for it. Autoregressive conditional heteroscedasticity. Sounds really fancy. But we still live in this world. We still use this assumption of a normally distributed return world when we're looking at analyzing how things work. And so let's move a little bit more. This is not in the textbook. This is my little kind of tangent. But I think it's important, and I think it's worth incorporating in a class where we talk about risk. So let's look at what happens if we look at really far in the tail, things that really shouldn't happen. So things that are 5 standard deviations away from the mean. These should really not happen very frequently. And so there should not have been any since 1950. And if we do the math to figure out, according to the normal distribution, how frequently they should occur, they should only occur about once every roughly 7,000 years. Empirically, in real life, they've happened 97 times since 1950. On average, about once every 13 months. Now that's on average. Sometimes they're back-to-back days. Sometimes they're 5 years in between them. And so I pulled just from Yahoo Finance the data for the S&P 500, and I essentially tried to estimate an empirical distribution, and I put it on this graph. It's the light blue line. That is the empirical, it's called the probability density function. And something you should very quickly notice. It has a much higher peak in the middle. It means that there are a lot of observations that happen within just one standard deviation of the mean. But then after that, it goes underneath the normal distribution, which is that dark blue line, which means that it's less frequent than the normal distribution here in the roughly 0.75 standard deviation away from the mean, all the way till you get to about 3 standard deviations. And then it crosses back over to be higher than the normal distribution in the tails. It's really difficult to see. So first thing I'm going to do is I'm going to smooth out that line a little bit. Here's a smoothed version of that line. Give you a better sense. Okay. Couple things also to notice. This is standard deviations away from the mean. Look at the peak, what's called the mode. It's not in the center. It's hard to tell here as well, but if you look at the tails, the one on the downside is a little bit bigger than the one on the upside. Is this what Robinhood CEO was talking about when he called GME a 5 sigma event? Yes. They're talking about standard deviations. And you want to know what? That's not even the biggest standard deviation move I've seen in the world of finance. Italian government bonds, the 2-year yield jumped. This was back in 2018, I believe. Daily move increased almost 200 basis points yield, 2 percentage points in a day. It was somewhere in the neighborhood of a 20-some standard deviation move. It was actually so high that you can't reliably estimate how frequently that should happen. The best estimate I could get, it should only happen once every 4.5 quadrillion years. Quadrillion. Big moves happen. And sometimes it's not necessary, it's just sometimes market mechanics. I'm not going to bore you with the mechanics of why the 10-year or the 2-year BTPs, Italian treasuries, move that much. So it's difficult to see on this graph. I'm going to, before we get to talking about other investments related but not related to the class topics, I just have, I think, 1 or 2 more slides. It's hard to see the level of the tails. And so what I did is I turned this into a log scale graph so you could better see how much different the smooth empirical and a log scale, and this is a smooth estimate based on empirical evidence. Look at how much higher that tail is on the downside and the upside. And again, it's hard to see here, but the tail on the downside is bigger. It's wider, or some statisticians call it fatter tails. It's called excess kurtosis, if you want to use the technical term for it. Excess kurtosis on both sides, and it's got skew, negative skew to the left side. Yet we still, as an industry, as a field, an academic field, really adhere to modifying our models and our estimates and our analysis to using a normal distribution. So, all right. I'm gonna, let's see, where do you think the 10 years going from here? I honestly don't know. I'm not even gonna try and guess. There's so many different things that are pressuring it, moving it different ways that I can see it going either way, going up to 3%, going down to back below 1%, and anywhere in between or beyond. Let's take a 15-minute break. So we'll come back around 7:20. Does that work for everyone? And